All right, so finishing up with this Extrema curve sketching, really long notes packet. Let's go ahead and finish it. I think we got these four more examples. And this one's kind of a good one because it's got a little bit of everything. We're going to take this function, figure out where it's increasing and decreasing. Remember, that's going to come from the first derivative being positive or negative. Then we're going to use that information to identify the relative extrema, the minimums and maximums. Then we're going to use the second derivative sign chart to figure out where it's concave up and concave down. And then also to use those intervals of concavity to figure out where we have points of inflection. And we're going to tie all that together and we're going to get a graph. Okay, so let's go for it. First thing though is let's get the first derivative. So if your original function is x to the 1/3 power, then your derivative would be 1/3. Am I on the screen? Nope. Good thing I should check. 1/3 x to the negative 2/3, which you could rewrite as 1 over 3x to the 2/3. Oh, sorry, I was about to sneeze and I didn't want to do that in the video. Okay, here we go. So we got the first derivative. Now let's go find the critical points, which are any x values that make the derivative equal to 0 or undefined. Now there's nothing that's going to make this derivative equal to 0 because the numerator is always 1. But I'm thinking if x is 0, the derivative would be undefined. So 0 is a critical point. So we're going to need to test it. Now let's just go ahead and do the second derivative stuff too while we're at it. So the second derivative, let's see, this negative 2/3 is going to multiply to the front, so it's looking like a negative 2/9 x 2/3 minus your 3/3 would be negative 5/3. And so again here you'd have a negative 2 over 9 x to the 5/3. And this is going to have the same special value, just x being 0. Remember, this is your critical point, or your stationary points. All the collection of the x values where the derivative is 0 or undefined, these are the things that could be maximums or minimums. There is no special word for the grouping of those important values for the second derivative, but it looks like 0 was also the only value. So that's good. 0 is the only value that's important for the first derivative, and then also for the second derivative. So let's do our two sign charts. F prime. And then we'll do the second derivative also, f double prime. And both of those, 0 was an undefined derivative. Now let's check. Like, does this point even exist? If you were to plug in 0 into your original function, let's see, the cube root of 0 is 0. So it's going to go through the origin. There is a point there. And then we're going to see, hey, is it a critical point? Well, we know it's a critical point. We're going to see, is it a max or a min? And then maybe it could also be a point of inflection. So let's go ahead and do this sign chart. So I need to test a point to the right of 0. So any positive number will work. Let's plug in something like 1, right? Just pick something that's convenient for you. So if I plugged in 1, 1 to the 2/3 power would be 1, and then 1 over 3 times 1 would be 1/3. So I know, hey, that would be positive. And if the first derivative is positive, that means your original function would be increasing. Very good. Now let's test something like -1. If I took -1, and you could either square it, then cube root, or you could take the -1 and you could cube root, and then you could square it. It doesn't really matter. Either way, if you take -1 to the 2/3 power, that negative is going to cancel, and you're going to end up just getting a positive 1, and then you have a 1 over 3 times 1. So once again, you would get positive. So it looks like this function is going to only be increasing, right? The derivative is always positive, except when it's undefined. So let's go ahead and answer some of these questions. F is increasing when the derivative is positive, so we would say negative infinity to 0 and 0 to infinity. Technically, you should probably throw out the value where x is 0, because at 0 it's not increasing, right? At 0, really it had an undefined slope. Okay, you could say f decreasing when f prime less than 0, and we say nowhere. It was never decreasing because the first derivative was never negative. And then let's say we only had the one critical point. Would it be a max, a min, or neither? Let's see, it was increasing and then it kind of stopped here. It was undefined slope for that one point, then it was increasing again, so it was going up, and then it was going up. So that's not going to be a max or min, right? That's going to end up being a neither. So we'll say F has no relative extrema. So all of the stuff about increasing and decreasing behavior and all the stuff about minimums and maximums, that's all getting answered from that first derivative sign chart. And then all of the stuff about the concavity and then points of inflection, that's going to come from your second derivative sign chart. So basically now we're going to go through and we're going to do this same exact process, but instead of doing the first derivative, now we're going to plug in to the second derivative. Okay, let us go for it. If I plug in a test point like 1 to represent this subinterval, let's see, 1 to the 5/3 power would be 1. So in the bottom you have 9 times 1, so the bottom's just positive. But the top is negative, so you have a negative 2 divided by a positive 9. So overall, that's going to end up giving you a negative output. And if your second derivative is negative, that means your function f is going to be concave down. Okay, and then let us test something like negative 1. Now, if I took negative 1 to the 5/3 power, again, you could cube root it and then raise it to the 5th power, or you could take your negative 1, raise it to the 5th power, and then cube root. When you have a rational exponent, it doesn't matter the order in which you do them. You can do the root, which is the denominator power, and then you could raise it to the exponent, or you could do the exponent first, or then you could take the root. It doesn't matter. Anyways, if I take negative 1 to the 5/3 power, let's do the denominator first. So if I took negative 1, and then I took the cube root of it, that would be negative 1. And then if I took negative 1 to the 5th power, it would still be negative 1. So here we go, negative 1 to the 5/3 power. This would still end up being a negative 1. So then the bottom would be a negative 9. So if you had a negative 2 over a negative 9, that would end up giving you a positive result. And if the second derivative is positive, that means your original function is concave up, right? So the first derivative tells you increasing or decreasing, which you use to potentially classify max and mins. Second derivative tells you concave up, concave down, which we use to potentially find points of inflection. So let's see, is 0, it wasn't a max or a min, is 0 a point of inflection? It changes from concave up to concave down, so yes, it will be a point of inflection. So let's answer the rest of this, and then we'll sketch it. F is going to be concave up when your second derivative is positive. So from negative infinity to 0, F is concave down when your second derivative is negative. And that was from 0 to infinity. And F has point of inflection when, and then there's a couple things you could say. You could say F changes concavity, that's fine. Or you could say the second derivative changes sign. Either one of those would be fine. The second derivative changing sign from positive to negative, or your original function f changing concavity from up to down. That's both perfectly fine justifications. But here we do have a critical point at x equals 0. Sorry, my allergies are working on overdrive today. Okay, so we've got all this stuff answered. Now we're just going to tie it together, and we're going to get the graph. Now we know, hey, we have this point of inflection. It's at the point 0, 0. We already checked for the y values. Now we should hopefully know some other points, like, hey, like this cube root function is going to more or less kind of come over like this. Like the cube root of 1 is 1, and then if I went over to 8, 2, that would be a point on the cube root function. 1, 2, 3, 4, 5, 6, 7, 8. And then symmetrically it would go to the other side as well. I think that was negative. 1, 2, 3, 4, 5, 6, 7. Okay, cool. So this function is going to look like this, and then symmetrically it's an odd function, so it'll look like this. Now, if you wanted to, you could have done your little curve sketching thing. You think about, okay, these little subintervals, like everything to the right of 0 is going to be one piece of the graph, and then everything to the left of 0 is going to be a different piece of the graph. So if you were thinking about this number line, how about from 0 to infinity, and then we could go from negative infinity to 0. Thinking about the combination of your first and your second derivative. Well, everything to the right of 0, your first derivative was positive, and then your second derivative was negative. So you would need the shape of the graph that's increasing, but concave down. And so that shape would look like that. And look, that is the shape that we have for that cube root function, right? It's increasing, the slope's always positive, but it's definitely got that concave down curvature to it, right? It's increasing, but at a decreasing rate. The slopes are getting smaller. It's still going up, but the slopes at which it's going up are getting smaller. So increasing at a decreasing rate. Okay, now if we looked at the other subinterval, which is everything to the left of 0, that's going to be your plus. First derivative is positive, second derivative is positive, so that's your increasing at an increasing rate. So it's going up and it's concave up, so that shape should look like this. And look, that is what the left side of this cube root graph looks like. This may not be as steep, or like this one's fairly shallow, but the idea is every single graph that you've ever done or that you will ever do will break down into little pieces, and each one of those pieces is either a straight line, which we really don't see much for curves, right? Those are typically just linear functions, because if you have a linear function, take the derivative, you have a constant, take the derivative again, you're going to have 0. Linear functions have 0 concavity, because if you take the derivative 2 times, that second derivative is going to be 0. So we don't really fuss with linear functions too often, because they're too easy to graph. Like Algebra 1 kids can do that. But if you think about all these other curves, for all these other functions in the whole entire world, they're going to break down into little pieces. And each one of those pieces is just going to be one of those 4 curves. And it's just going to be, hey, which curve? Based on the combination of the signs of these first 2 derivatives. Like that right piece was this combination, then the left piece was this combination. Right? And every single graph will always break down into little pieces, just like this one. And then you just figure out, hey, which one of those curves fits in each piece. Then you connect them all together, and that's how you can get a pretty good sketch of any graph of any function. Right, cool beans. Let's go ahead and let's do the next one. So we have this function, x minus 2 cubed. Sorry, I kind of wrote over it a little bit. I have this function, x minus 2 cubed, and the domain, it tells me, is from negative infinity to infinity. How wonderful. Find the intervals where it increases, decreasing. The extrema, where it's concave up, concave down. Oh, it doesn't even ask for point of inflection, but we're going to do it anyways. Right, so basically do everything for this function. Now this one's a little bit annoying. Oh, actually, it doesn't even tell me what the function is, right? It gives me what the first derivative is. So it says this f prime, I didn't see that, f prime is x minus 2 cubed. Now I'm going to go ahead and I'm just going to like speedily expand it. Later on, once we learn something called chain rule, we'll be able to take the second derivative no problem. But for now, I'm just going to multiply it out. So this first derivative, if you were to multiply it out, it's going to end up being x cubed minus 6x squared plus 12x minus 8. Okay, you can use binomial theorem to expand it, or you can just multiply it out the 3 times. I've already done it. I have the answers on my little scratch work, so I'm not going to. Right? I'm just going to show you what the answer was. All right, so that's your first derivative, and then expanded. There it is. So let's go now find the second derivative. I'm just going to take the derivative while it's expanded, so we'd have a 3x squared minus 12x plus 12. Which you could factor. It looks like we could factor out a 3. And then it looks like that's going to factor minus 2 minus 2. So it looks like it's 3x minus 2 squared. Right? Kind of look at this. You have something to the third power. You have 3 something squared as the derivative. Yeah, we're going to learn really how to do that. Take the derivative while it's factored. We're going to learn how to do that in a following lesson. But we have the first derivative. That was given to us. You can expand it, take the derivative while it's expanded, then refactor it back together. And then we have an expression for this second derivative. So that's very good. Let's go ahead and do the 2 sign charts and then answer all the questions that this question wants us to do. Here we go. So the only critical point, I think, for both of them is going to be 2. Right? If I plugged in x equals 2, that would make the first derivative 0, and if I made the second derivative have an x value of 2, it would also make the second derivative 0. So let's now test. We'll do this first derivative sign chart, then we'll do the second, then we'll answer all these questions, and we'll sketch the graph. Okay, here we go. Let's plug in something to the right of 2 into this first derivative. Something like 3 or like 30. That would be fine, or 100. Doesn't matter. Any number bigger than 2 is going to be fine. Just pick something that's convenient and easy for you to do, like 3. Okay, 3 minus 2 would be 1. 1 cubed would be positive. So that's great. If I plug in any number bigger than 2, that result from the first derivative is going to be positive, which means your original function is increasing. If I plug in something less than 2, like 0, you'll see you'd have negative 2 cubed, which would be negative 8. So you would get a negative output, which means your original function is decreasing. So we know where it's increasing, we know where it's decreasing. Let's try to classify this as a min or a max. Look, your derivative changes from negative to positive. So that means your slopes were negative. That function was going down. Then it stops, and it turns, and it begins to go up. And if your function changes from decreasing to increasing, we can visually see that that point, I don't have the equation for the f function, but I know that point at x equals 2 is going to be a minimum. It was a critical point, and then it ended up being a minimum because of the way of how that behavior changed. Okay, let's go ahead and do the second derivative. If I plugged in something like 3, 3 minus 2 would be 1, 1 squared would be 1, 3 times 1 would be 3. Okay, that's positive, so it's going to be concave up. And then if I plug in something like 0, let's see, that negative, when you square it, would cancel, so you have 4 times 3, that's going to be positive also. Right, so it's concave up for this piece, and it's concave up for this piece, so this would not be a point of inflection. Right, and you really shouldn't ever have something that's a min or a max and a point of inflection. It's kind of going to be an either or. Like here, this one was neither, but it was a point of inflection. This one was an extrema, and so it should not have ended up being a point of inflection. It wouldn't make sense to have a min or a max that is also a point of inflection. Right, it's kind of going to be exclusive, one or the other. Let's answer all these questions, and then let's sketch the graph. Here we go. F is increasing. F is increasing when, am I on the screen? Yep. F is increasing when f prime is positive. I always like to write those justifications because your IB exam always likes to say something like explain your reasoning or justify. So just saying something like, hey, your first derivative is positive, you're going to get all those justification marks. F is increasing when f prime is positive. We know that happens everything bigger than 0, or bigger than 2, sorry. F is decreasing when f prime is less than 0. So that was everything to the left of 2. Let's see. This does have us identify a min, or it wants the extrema. So say f has relative min at x equals 2. And we could say by first derivative test. Okay, so that's good. I'm running out of room. Let's go ahead and do the concavity. F is concave up when your second derivative is positive. So that was everywhere to the left of 2 and everywhere to the right of 2. And then F is concave down. I really should space these notes out a little bit better. Oh well. F would be concave down when the second derivative is negative, so that would be nowhere. And then I'm running out of room. We'll just say F has no point of inflection. And I'll just kind of throw that in there also. So I've got all this answers kind of somewhere eventually squeezed on the page. Now let's take all that and let's sketch it. Here's 2. Now 2 is not an asymptote. I just kind of like to visually see kind of where that dividing line is, because this graph is going to break down into 2 pieces. There's the piece that's going to be to the left of 2, and then there's going to be the piece that's to the right of 2. And we just have to figure out which shape it's going to be for each of those little intervals, and then we'll be able to sketch this graph. Let's actually plug in, actually we don't really know any point on the function. Right? Like it doesn't say, oh, f of 2 equals 1. So we really don't know any y coordinates of this graph. So I'm just gonna wing it. Like I'm just gonna start here. It doesn't matter. It really doesn't tell me if f of 2 is 1 or if it's 5 or if it's negative 7. I don't know. But we need to start somewhere. And then from this, we're going to do one of my 4 shapes. And then from this, we're going to do one of my 4 shapes. And then we need to figure out which shape is which. So let's go for it. We have negative infinity to 2. We need to figure out what's the combination, and then from 2 to infinity. Okay, so let's see. Everywhere to the left of 2. Let's do to the left side first. Let's see. Your first derivative was negative, and then your second derivative was positive. So this one has to be decreasing, but concave up. So if you think about, let's see, where's my combinations? We need decreasing, but concave up, the negative positive case. So the graph is going to look like this to the left side of 2. And then everything to the right of 2, it's the plus case. So it's positive, increasing, and it's concave up. So that one's going to look like this. So see, in this interval, I need a shape like this. And then in this interval, I need a shape like this. So this one's just going to end up looking mostly like a parabola, or it could be like an x to the 4th. But generally, we could sketch a pretty good graph. It doesn't have to be super precise, right? That keyword sketch means it doesn't have to be point for point precise. We don't even know where the y coordinates are. We're just kind of getting the general shape of this right. And so that's how we go ahead and we do this curve sketching. We just figure out, hey, what's the combination between those two derivatives? And then that will tell me what the individual shape is for all of those subintervals. Now, this one wasn't too bad because you only had the 2 subintervals. You could have a much more complicated function that breaks down into more pieces. But the idea is any function that you have ever done or will ever do will always break down into little pieces, and all of those pieces will just be one of those 4 shapes, right? And those 4 shapes form the circle, and which of the 4 shapes is just dictated on, hey, like what's the combination between the first and the second derivative as far as plus, 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 minus, minus, plus, or minus, minus. All right, 2 more examples, then we're done. Okay, let me try to keep this on the screen because I have been having a really mighty struggle doing that the last 2 days or so. Oh well. Sketch the graph of a function that fulfills the following criteria. It says the domain is from negative infinity to 4. The range is from negative infinity to 3. So first thing I would do is have these restrictions. So I'm going to come over here to 4. 1, 2, 3, 4. And then I know kind of my graph should not exist anywhere to the right of this. So I'm just going to kind of shade this so that I don't graph anything there. Right? It says the domain is everything less than 4. So I'm just shading this so that I represent like, hey, like my graph should not exist there. And then we had the range, it was negative infinity to 3. So let's come up to 3. And then the graph shouldn't exist anywhere up above it. Okay, cool. So we know the graph is only going to live down here in this area, just based on the domain and the range. So that's good. Got that kind of taken care of. It says your derivative is positive on these intervals, and it's negative. Let's take that and let's translate it into a sign chart. So from negative infinity to negative 2, and then I think from 4. So I think we got negative 2, 2, and 4. It looks like the derivative was positive, and then, ooh, I need a 0 also. Darn it, I thought I had them all. We need 0 also. 0, 2, 4. So on this piece, it was positive, and on this piece, it was positive. And then let's see, negative 2 to 0, it's negative, and 2 to 4. Oh, that's right, and we don't need this piece because of the domain. Okay, cool. So it's going to be increasing, decreasing, increasing, decreasing, right? That's basically what that piece tells me. Then it says the derivative is equal to 0 at these 2 points. So you have your horizontal tangents. And then the derivative does not exist. It's undefined. So you have something like a cusp or a sharp turn there. Okay, so we've kind of gotten all that information. Let's go ahead and do the second derivative also. It says your derivative is less than 0, basically everywhere. Second derivative. Remember, your domain ends at 4, so we don't need anything to the right of 4. And then 0 was also a point. Let's see, it's negative, negative. So that second derivative is negative, so except at 0, it looks like. So the graph's always going to be concave down. Would this be a point of inflection? No, because it's concave down on both sides. And then, oh, here we go. We got some coordinate points. That's great. F of negative 2 equals 3. 1, 2, 1, 2, 3. And then 0, 0, 2, 2, and 4, negative 1. Okay, so let's now try to connect all these pieces and figure out what this graph is going to look like. Let's just do it one subinterval at a time. Well, I'm just going to start on the right. And the rightmost piece, right, is going to be from 2 to 4. And then we'll have the piece from 0 to 2. and then we'll have the piece from -2 to 0, and then we'll basically have the rest of it, right? So we have this first interval, what shape is going to connect those 2 points? Then we have that second little interval, what shape's going to connect those two? Then this one, and then everything to the left of it, right? Anytime either of these two derivatives changes something, changes from a positive to a negative or negative to a positive, that would need to break and cause you to have a new subinterval. So basically, any of these numbers have to split up your intervals. All right, let us go for it. Let's do the right side first. So the right side between 2 and 4, the first derivative was negative. That second derivative, right, 2 and 4 would also be negative. So that's your negative case. So that's going to be decreasing and concave down. So that's going to look like this. So I know this type of a graph. There you go, right? It's going to look something like this, right? It has that type of a shape since it's the negative combo. Moving on, let's do the next one. Between 0 and 2. 0 to 2, your first derivative is a positive. And between 0 and 2, that second derivative didn't change. It's still negative. So that's increasing, but is concave down. So that one's going to look like this. So here we go. Connect it, make that type of a shape. 2 intervals down, 2 to go. Let's look at this next one between -2 and 0. Let's see, it's going to be your negative case again. So here we go. Something like this. And then everywhere to the left of -2, it's going to be your plus, minus. So that one's going to look like this. So here's a pretty decent sketch, right? It may not be super precise. I only knew where the 4 points were. Like all these other ones, I was just guessing. I was just sketching. Let's kind of check and make sure that this does satisfy everything. Does it have the required domain? Yep, it looks like this domain is everything up to and including 4, so that's good. Actually, I guess technically, since it's a parentheses, well, I'm just going to change this to a bracket, just so I don't have to change the solid dot to an empty dot. I'm just going to leave it like that. Change it to bracket so it's inclusive. All right, but it definitely meets the domain, the range, -infinity up to 3. Yep, that's good. Let's see, your function is increasing on this interval and this interval, and then it's decreasing from here to here. Yep, that looks good. Let's see, your derivative is 0. That means you have a horizontal tangent at this point and at that point. That looks good. And it says your derivative does not exist. Yep, it looks like we have a little cusp. So that all is good. Then it's concave down on this interval and on this interval. Sure. And then, of course, we have the coordinate points. So always make sure that at the end, your result matches with all of those criteria this question started you with. This one here, the graph that we've produced, it definitely does. Okay, last one. Given the graph of f prime below, right, always pay attention. This graph is labeled as f prime. Always pay attention to what the graph is labeled as. Here, it's giving you f prime, and then it's asking you to sketch a possible graph of the original function f. And it says it's continuous, so there's not going to be any holes, any jumps, or any asymptotes, or any other discontinuities, and it has a domain and a range from -infinity to +infinity. Okay, wonderful. Well, let's look at this one. Here we go. Let's think about what this first derivative is going to tell me. Let's see. When the first derivative is 0, f has a horizontal tangent, right? It's critical points. So let's see. I think right here at x equals 4, your function is going to have a horizontal tangent. And then let's see. The derivative changes from positive to negative, right? It starts off above, then it crosses, then it's below. So this point where the derivative is 0, I know your original function is going to have a horizontal tangent. It's either going to be a max or a min, and then it changes from positive to negative. So that means f changes from increasing to decreasing. So I know you're going to have a relative maximum at 4. Just based on this information, that this is an x-intercept and it crosses from above to below, I know f is going to have a maximum at 4. Okay, and then let's see here. F would be increasing when your derivative is positive. Let's see, so that's going to be all on this interval. So from -infinity to 2, and it looks like from 2 to 4, right? Even this chunk, right? This graph has a negative slope, but you're thinking, hey, this function, this f prime, it's above the x-axis, so f prime is positive. Therefore, your original function, which we cannot see, is going to be increasing. F would be decreasing when f prime is less than 0, so that's only going to be to the right of 4. So from 4 to infinity. Okay, and then let's see, we could try to answer questions about concavity too. Remember, the concavity would be, are the slopes of this positive or are the slopes of this negative? But let's just kind of try to take all of this stuff and see what we can do. I'm going to erase what I've done so far just so it stops to clutter my graph. Okay, so I know I've got a maximum at 4. I don't know where the y-coordinate is, but that's a good place to start. Like, I'm just going to put some type of a maximum. How about here? We'll put it at 4, 5. Why not? Now let's think. Everywhere to the right of 4, let's see, the derivative is negative, so that graph is going to go down. It starts off with a small negative value. So it starts off with a small negative slope, and then it looks like it gets bigger negative, so this graph should get a little bit steeper, and then the biggest negative value is right here at 6. So that's when the graph should be the steepest, and then it looks like it kind of just tapers off and has something kind of like this. The graph is still going to be negative, so this graph should keep going down, but the steepest slope in the negative direction should happen right here, which, I don't know, I kind of got maybe a little bit off. Here, let me move it. There we go. So since this function, the derivative, since it's negative, since it's beneath the x-axis, my original function f needs to be decreasing, and then however far below it is, right, the farther away from the x-axis your derivative is, the steeper your slopes for your original function should be. Now let's look at this point between 2 and 4. It says your graph, right, since this is positive, you know the graph is going to be increasing, and it looks like, hey, like this graph gets pretty steep. So this graph always needs to be increasing, and then right here, really, it needs to be almost vertical, right? Since this slope is going up towards infinity, and this slope is going up towards infinity, right? Since the derivative is getting infinitely big, that means the slope at this point should be vertical, right? So the slope at this point is vertical, and then it's going to gradually taper. And then you have your maximum at 4. Here again, it's still going to be positive, so the graph is going to look something like this. And then it looks like here it's getting pretty close. Really, like the slopes are getting smaller and smaller and smaller. It's still positive, but right around here, right, it's just a barely positive slope. So your graph is going to kind of level out, and it's going to get pretty flat. It is still going to be slightly increasing, but not very much. Right, so this one is pretty weird. I wouldn't really stress too much about it. You're not really ever going to have to do stuff like this again. But it's kind of nice to know that you could, right? If you're given the derivative, you can figure out all sorts of stuff about the original function. And then you could use that information to make a fairly decent sketch. Really, I think this actually is a typo. You shouldn't have a range that's up to infinity. You should have some bound, right? We have a maximum here, and that's actually the highest the function's ever going to get. So there was a typo in this question. That's why I really didn't want to fuss with the domain and the range. But clearly the domain is negative infinity to positive infinity, and the range, it will go down forever and ever and ever, but it should actually have a maximum value. And again, I didn't know what that maximum value was here. I just assumed that it was 5. So I just put that point at 5. All right, so there's curve sketching. The next notes video is going to kind of go through a smaller notes packet, also over curve sketching. So please make sure you watch that next one also, because this stuff is weird and it's conceptual. Just remember the basics, right? This packet is a little bit weird. Just remember the basics. The first derivative sign chart. That is how you find increasing, decreasing, and then you use that change of that behavior to classify mins, maxes, or neither, right? And the critical points is the collection of all of those special values, anything that makes the derivative 0 or undefined. For your first derivative, those are called critical points. Those are all the things that might be mins or maxes. And then spoiler alert, most of the time, the things that are neither, most of the time, those end up being points of inflection. But you don't really know that unless you go on to do the second derivative. derivative sine chart. But this first derivative sine chart, doing this sine chart, figuring out where it's positive, where it's negative, that tells you all the intervals of increasing and decreasing behavior, and then you could use that sine chart and interpret the change to figure out where you have maxes and where you have minimums. So that first derivative is useful, right? Increasing, decreasing, and mins and maxes. Your second derivative sine chart, which is not called the second derivative test, right? We had a different thing for the second derivative test. We did that at the tail end of the last video. Your second derivative sine chart is still very useful. You would collect all of those important values. Again, there's no name for them. Just call them important values or special values. They're not critical points. Critical points is this, but for the first derivative. These important points for the second derivative, those are the things that might be points of inflection, but you would still have to test, right? You throw them all down on your number line. You test them for positivity. If the second derivative is positive, that means concave up. Second derivative negative. And then whenever there's a change in the concavity, you have a point of inflection. So that second derivative sine chart is really good. That's how you answer intervals of concavity. That's also how you potentially find the points of inflection. Very, very, very nice. So the combination of doing both the first derivative sine chart and the second derivative sine chart, that's how you get a ton of information about that original function. And you can use that and those 4 basic curves, you can use that to get a good sketch.